Hello and welcome to this video on writing inequalities involving the word and compactly. Alright, so what we mean by compactly here is if I have a compound inequality involving the word and there's some overlap where all the solutions of the compound inequality fall between two numbers. So say between 1 and 4, or all the solutions are between 2 and 7. There's a way to rewrite the compound inequality instead of having the word and as a single inequality, a nice compact inequality. All right, so I'll just have a few examples of that. All right, let me show you. So for each of these inequalities, compound inequalities I'll be showing you, I'm going to be asked to solve the compound inequality, express the solution set using set builder notation and interval notation, and of course graph the solution set. And these are inequalities involving a single variable, so when I draw the graph of the solution set it'll be on a single number line. Okay, so this is what I mean by a compact inequality, or this is an inequality written, a compound inequality written compactly. Okay, it's two inequalities that I've written as one simple statement. And these compactly written inequalities, right, these are reserved for an and, compound inequalities involving the word and, not the word or. All right, and we'll get to compound inequalities involving the word or in a future video. All right, so this let me write out what we're seeing here on a separate page, right? So you see this is -2 is less than 3 times x plus 1 and 3 times x plus 1 at the same time is less than 10. And this can you can also check to see that your compound inequality like this is making sense, because if you look at this from left to right, we are seeing that the number on the far left is indeed less than the number on the far right, right? -2 is less than 10. All right, so this actually kind of makes sense to put a compound inequality compactly like this. So let me make a little statement here about these compact, and inequalities. Before we go into solving it, right? So if I have two numbers that are, one is less than the other, say a and b. So suppose a is a number and b is a number, and a is less than b, on the left of b on the number line. And I have another number called, x, or another set of numbers represented by x. If x is greater than a and x is less than b, all right, so this is my compound inequality right here. X is greater than a and x is less than b. All right, so here's the compound inequality connected by the word and. All right, well, what we'd be seeing on a number line is the following, right? If I were to draw a real number line, say here's 0, and again, the numbers, I don't know what a and b are. All I know is that a has to be less than b here. We'd be say a is on the left of 0, and say b is over here. As long as a is to the left of b, this compound inequality, the solutions to this, all the numbers that are greater than a and numbers less than b at the same time, well, that's all the numbers in between a and b. again, not including A, right, is just greater than A. So just to the right of A, and not including B, right, just the numbers less than B. And remember, in a previous video, I solved compound inequalities involving the word and what you did was you took these numbers and these numbers, and you found their intersection, right, the intersection, the numbers that satisfy both at the same time, and that would be these numbers in between. So when there is, when the solutions are between two numbers, so when the solutions are between, that's key, between two numbers, then we can write the two inequalities as a single inequality with the two symbols as a compact inequality. Then you can write a compact inequality. And that's the only time. Alright, so I'm going to put a little bubble around this. Alright, this is very important. Okay, this is the only time we're going to be writing these compact inequalities that look like this. So if I have one number less than another, and then there's this compound inequality, all the solutions of this compound inequality fall between these two numbers, then you can make the following statement. A is less than X and X is less than B. This is just another way to write the same statement. This is X is greater than A. You're seeing X is greater than A here, just written the other way. And X is less than B at the same time, and you're seeing X is less than B right here. And it's connected. And this is just saying that, the value of the solutions, right? The solutions are between two numbers A and B. And again, this number on the left here has to be less than the number on the right. It has to actually make sense, right? So like, for example, this would be good. A good compact inequality, 1 is less than X, and X is, say, less than or equal to 3. See, the number on the left here is less than the number on the right, so it actually makes sense to say this. And this is all this is saying is my solutions are between 1 and 3, not including 1, right, because there's no equal to, but including 3, right, there's the equal to 3 part. And then this would be bad right here. If I said 5 is less than X and X is less than 2. If I connected two inequalities like this, this doesn't make any sense, right? Because the number on the left, 5, is not less than the number on the right, 2. 5 is not less than 2, right? So this makes absolutely no sense, and I wouldn't consider it, right? It's got to be set up so that the number on the left is indeed less than the number on the right if you have all these less thans here. Same thing when if I drew them in the other direction. If these were all greater thans, the number on the left would have to be greater than the number on the right. Again, if I change the direction of the inequalities. But just be careful when trying to connect them. You can only draw a compact inequality like this when your solutions are between two numbers, right? This is implying betweenness here. Okay, so back to my problem. All right, back to the example. We're asked to solve this inequality, right? Find the solutions. What can I replace X with and make this a true compact statement, a true inequality, where negative 2 is less than this number and this number is also less than 10 at the same time. Alright, so one way we could do this, I guess I'll call this method 1, is to actually rewrite the inequality with the and solve it the way I've done in a previous video where I solved inequalities involving the word and. So rewrite using and and solve. So let me do that. So this is saying that negative 2 is less than 3x plus 1 and and these compact inequalities like this are always and inequalities. And 3x plus 1 is less than 10. Okay. This statement means exactly the same as this statement with the and involved. All right, remember how this worked. We solved each inequality separately. So I'll do the left here. I would subtract 1 from both sides, and that's just subtraction, so the direction of the inequality does not change. So it's negative 3 on the left, still is less than, and then 3x on the right, and then I would have to divide by positive 3 on both sides to get x alone, and that is a positive number that I'm dividing by. So the inequality again does not change. So negative 3 divided by positive 3 is negative 1 is less than, and then the 3's cancel and I have x. So negative 1 is less than all the solutions of this left inequality. So you could also write this, sometimes people like the variables on the right side. So if I read this from left to right, it says negative 1 is less than x. We'll read it the other way around. That would be x is greater than negative 1. So you could switch sides, but if you switch sides, you also have to switch the direction, right, of the inequality symbol. So these mean the same thing. Okay, and I'll solve this inequality over here. So first I'd subtract 1 from both sides, right, leaving me with 3x on the left. Still is less than, because all I did was subtraction. 10 minus 1 is 9. And then dividing both sides by 3. Again, that is a positive 3, so this still doesn't change the inequality symbol. So I have x is less than positive 3. Don't forget the word and is here. So we're looking for the intersection. Alright, so I'm going to draw a little picture of a number line where we'll put up the solutions to both these inequalities and see where the intersection is, see what numbers satisfy both inequalities at the same time. So here's a number line representing all the real numbers. I'll put 0 somewhere to separate my positives and negatives. I did in this little fuchsia magenta color here the solutions to this first inequality. So that's involving the number negative 1. Negative 1 is to the left of 0. And all the solutions of this first inequality, right, the left one, sorry, I'll put this down here, the left one, all these solutions are numbers greater than negative 1, but not including negative 1, right? So negative 1's not there, so I put a little open circle above it, saying that negative 1 is not a solution. And then all the numbers that satisfy this are greater than negative 1, right? 0, 1, 2, all these numbers over here. All right, so these are solutions of, I'll say the left inequality. I'll just put left, right? And I'll write the word inequality because it's pointing right and it looks like I'm saying it's pointing left. Left inequality. All right, and then in the light blue color, I'll draw the solutions of those below, and we'll see the overlap, the intersection. All the numbers less than 3, right? Now 3 would be to the right of 0, right? To the right of negative 1. All the numbers less than 3, but not 3 itself, right? So again, another open point there. And all the numbers less than 3 that satisfy this are, 2, 1, 0, all these numbers to the left here. All right, so all these numbers satisfy the inequality on the right, right? This 3x plus 1 is less than 10. I'll say that's the right, all the solutions of the right inequality. All right, and then we're looking for the overlap, right? What numbers satisfy this inequality and this one, right? You're looking for the intersection. So hopefully it's obvious that it's all these numbers in between negative 1 and positive 3 that belong to both sets, all right? But not negative 1 itself, right? Negative 1 belongs to this second set, but not the first set. and not 3 either. 3 does, 3 belongs to the first set, there it is, but it doesn't belong to the second set. So the only ones that actually belong here are these numbers in between -1 and 3. Okay, great. So now that I have the solutions, I can express them in the ways that were asked for. So one was called, well, I like to make the graph first. I personally like making a graph of the solutions to an inequality before I write it out in any other way. All right, so a graph of the solutions, here's a number line, and pop 0 somewhere to separate positives from negatives, and our solutions are just, again, all these numbers that are in the intersection of these two sets, the numbers between -1 and +3, right? But not -1 and not +3. So I'll put little open points above those, or if you want, parentheses, right? And then every number in between gets marked, and there's a graph of the solutions of this compound inequality, right? So this here, or again going back up to the way it originally looked, take any, test it out. Take any number between -1 and 3, 0, 1, 2, 1.5, 2.7, -0.78. Any number, any real number between -1 and 3, and plug it in for x. So I'll try that with an easy one. Now, how about just 1 or 0? I'll pick 1. 1 is between -1 and 3. 3 times 1 is 3, plus 1 is 4. Is 4 between -2 and 10? Yes, it is. Right? So 1 works, and you can try it out with any number between -1 and 3. This will be a true statement. You'll get a number in here that's between -2 and 10. Great. So here's a graph. I'll put this in a box. Right, that's part of what we were asked for, part of our solution. We were also asked to write the solutions in what's called set builder notation. So this is just another way to describe the solutions, the same set of numbers that are between -1 and 3. So this is a set, right? So I draw the little curly braces to start a set. And it's a set of what? It's the set of x values, right? Where our variable in this inequality is x. The set of x values, right? Set of values of x such that, right? There's usually a little bar or a colon, right? 2 little dots to separate, what the set elements look like, and then a description of them. All right. So here's where I'm going to write my compact inequality. Right, the solutions are these values of x. Right, these values of x that are both greater than -1 and at the same time less than 3. Right, that's between two numbers. Right, all my solutions are between two numbers. As I mentioned on a previous page, that is the only time you can write these compact inequalities, is when our solutions are between two numbers. So I'm between -1 and 3. So you see -1 is less than x, and x is less than 3. All right, that's again these two inequalities right here. -1 is less than x, and x is less than 3, written in a compact way. All right, and again, double check. Is the number, if I'm doing all the is less thans, is the number on the left really less than the number on the right? Yeah, -1 is less than 3. So this is good. This is another way to describe all the numbers between -1 and 3. All right, so there's another part of our solution. Now these mean the same thing. They say the same thing. And then one other way to represent an infinite, a set of infinite solutions is with something called interval notation. All right, so what I'm going to write down here is an interval. And I've put up videos in the past on writing solutions, writing sets in interval notation, so you could look those up. Just look up interval notation in your search bar. I'm not going to go that in depth into it here. But you look at this graph. I like to look at a graph when I'm writing an interval. and this graph has just one piece to it. Right? There's no piece of the graph out here, there's no piece of the graph out here, there's no break in this, it's just one solid piece. And we first write the left end of that piece. The left end is at -1, comma, and then is there a right end to that piece, a high end? That'd be at 3. And then we cap off these two numbers, the two ends, with either a parenthesis or a square bracket, rectangular bracket, depending on whether or not that number is actually part of the set. So -1 is not part of the set, right? -1 is not a solution. So to indicate that a number on the end is not a solution, you put a parenthesis. Same thing for the 3. 3 is not in the set, so I put another parenthesis. Right? And then these set of parentheses indicate that every number between -1 and 3, from -1 up to 3 is a solution, just not those two themselves. Okay, that's called an interval, right? Interval notation. And all three of these things, this interval, this set here, all the x's that are between -1 and 3, and this graph, right? They all show the same numbers. They're all describing the same set of numbers, all the numbers between -1 and 3. All right, great. So that's one way I could do this, right? Where I'm asked to. Sorry, I'm going to pop this back now. All right, I was asked to solve this, compact inequality, this compound inequality, and because it's connected and compact like this, I know the word "and" is involved, right? So that was one way to do it, was actually split them up. Split up the left inequality from the right inequality, and then solve each of those, and do what I just showed you to get our solutions here, the numbers between -1 and 3. Another way to do it, all right, I'll do this same example in a second method, was, do you notice how when I did the first method here, when I split them up, you see how I solved the left inequality and then I solved the right inequality, and then we found the intersection, right, of the solutions of each inequality, and found that those numbers between -1 and 3 were the solutions. Well, you see the steps I followed in each of these. First I subtracted 1 and then divided by 3. And for the right inequality, I also subtracted 1 and then divided by 3. So I was being kind of redundant. I was doing the same steps again. So rather than split them up and do the same steps multiple times, the second way you could do this is just keep it together. All right, so I'm going to cover this up. We'll do this. This is method 2 for solving these compact compound inequalities involving the word "and." Method 2 is keep it compact and perform the same steps. We're going to basically be solving the left inequality and the right inequality at the same time, performing the same steps and getting the variable alone in the middle. So keep it compact and isolate the variable in the middle, right? So that it's between two numbers, and we're going to end up seeing that x will be between -1 and 3, as we said earlier with the solutions. Isolate the variable, in the middle part. All right, so I'm going to write this again. We have -2 is less than 3x plus 1, and 3x plus 1 is less than 10. And again, this actually makes sense because -2 is less than 10. This is okay to write this. And I'm going to keep this the way it is, and I'm going to get the variable alone, the variable x alone, in the middle. And what I do is I'm going to solve both inequalities, the left inequality and right inequality, at the same time, performing the same steps. So what would I do for this left inequality, right, is I'd subtract 1 from both sides. And I'd do exactly the same thing for this right inequality, right? I'm subtracting 1 from this, so I got to subtract 1 from this side of this inequality as well. So basically, what I do to the middle, I'm going to do to the outsides as well. All right. So that's just subtraction, so the inequality's directions don't change, right? So we have -3 over here, is less than still, and then 3x in the middle now, and is less than, 10 minus 1 is 9. And then I want x alone in the middle, 1x, not 3x, so we divide by positive 3. And again, if I'm doing this left inequality, I'm dividing both sides of that by positive 3. If I'm doing this right inequality, I'm dividing both sides of that by positive 3. All right, so again, what I do to the middle here, I'm going to do to all three parts, the middle and the outsides. And this is division by a positive number, so the inequality direction will not change. And I'm left with now negative 1 on the left is less than x in the middle, and that's also less, and that's less than 3 on the right. And there we go, right? Variables alone in the middle, and do you see how this is exactly what we got earlier, right? When we split them up. And here are my solutions, right? Compare that to what we got earlier. Here's a graph, right? This is x can be any number, this is between negative 1 and 3. It's greater than negative 1 and at the same time less than 3. And there's a picture, graph. Set builder notation, all my solutions for this inequality are, any value of x, as long as that number is between negative 1 and 3. I write this inequality here, the description of the solutions. And the interval, again, everything from negative 1 to 3, just not including 1 and not including 3, right? So parentheses on those. I got exactly the same thing in a much faster fashion with a lot less writing, right? I didn't write this inequality and that inequality and then write the same steps twice, right? And then found the overlap and all that. We see what the overlap is when we solve it, these compact inequalities this way. Okay, so this method is what I'm going to stick to for my last couple examples. Okay. So my next example, I have another one of these compact inequalities, right? So it's an AND inequality, right? This is 0 is less than 4x minus 5, and 4x minus 5 is less than or equal to 3. All right, so again, a compound inequality with the word AND just written in a compact fashion. And it makes sense too, right? Because look at the outside, 0 is indeed less than 3, right? So it actually makes sense to write a compact inequality like this. And I'm trying to find the solutions. So I'm going to do that method 2, that second way, where instead of splitting them up with the word AND, right? Just remember that the word AND is there, and I'm just going to keep them the way they are. And solve for the variable, get the variable alone in the middle, right? So it's like I'm solving both inequalities at the same time, right? So if I were solving this left inequality, right, 0 is less than 4x minus 5, the first thing I would do is add 5, right? So I'm going to add 5 to the middle, add 5 to the left there, and if I'm doing that to that left inequality, I'm also doing that to the right inequality, right? Adding 5 to that part too. All right, so then after this we have 5, it's just addition and subtraction, so these inequality symbols won't change direction. So 0 plus 5 is 5. Still is less than, and when I add 5 to the middle there, I'm left with 4x. And that still is less than or equal to, and then 3 plus 5 is 8. Wonderful. Alright, and then again, if I was solving this left inequality and I want x alone, I'd be dividing by positive 4. Same thing for this right inequality. If I want x alone, I'd be dividing by positive 4. So I'm doing that to all three parts. Dividing by positive 4, dividing by positive 4, dividing by positive 4. Alright. Now that is again a positive number I'm dividing by, right? So the inequality direction does not change. So the left side is the number, 5/4. Or 1 1/4, or 1.25 if you want to write some other way, a mixed number or a decimal. But 5/4 is a nice simplified fraction. I'll leave it that way. So 5/4 is less than still, and then 4 cancels here, and then you have 1x, which I want in the middle, and is less than or equal to still, and then 8 divided by 4 is positive 2. And here we go, right? The variable is alone now in the middle. I have solved both inequalities at the same time. Okay, and then over here on the right side. Let me put up all the 3 different ways they wanted us to represent these solutions. So first I'll draw a graph of the solution set. So here's a number line. And pop in 0 there somewhere, and our numbers here, this is telling me my solutions are between 1 1/4, 5/4, and 2. So I know 5/4, that's positive, so it's going to be to the right of 0. There's 5/4, and then 2 is even bigger than that, so it's going to be to the right. Let's say it's over here. I know it's not perfectly spaced the way I have it written here, but there's 2. And this is every number between. Right, every number between 5/4 and 2 will work. A little there. But what about 5/4 itself? What about the ends? Well, 5/4 doesn't satisfy the left inequality, right? 5/4 is not less than 5/4, it's equal to. And this doesn't have that or equal to part. So I put an open point, an empty point above 5/4, indicating that 5/4 is not a solution. Or again, you could put a parenthesis on the graph if you want to indicate that it's not a solution. And then what about the other end? 2. Well, 2, is between 5/4 and, it's not between them, but it's greater than 5/4. It satisfies the left inequality, and it also satisfies the right inequality. 2 is not less than 2, but 2 is equal to 2. It's got the or equal to part. So 2 does satisfy this statement, satisfies both of them, so I'll put a solid point there above 2, right, to indicate that 2 is a solution. Or you could put one of those rectangular brackets, right, to indicate that 2 is a solution. But there's the graph of my solution set. Then again, I could also write this in that's called set builder notation. All right, so the set of all the solutions is this set here. It's the set of all. Now the variable involved here is x. So it's the set of all real values x, such that, and then I'll just write my compact statement here, such that x is between, a little less than, sorry, that's a less than there. 5/4 is less than x, and x is less than or equal to 2. I'm just writing my statement here as the description of the solutions in this set notation. Right. Now, again, you could also write, 5/4 is less than x, and the word and then x is less than or equal to 2 if you wanted, but it's much simpler and quicker to write it this way. And this still does make sense, right? The number 5/4 is indeed less than the number 2, so you're still good here. And then the final way was, as an interval, right, in the interval notation. And looking at my graph, again, there's only one piece to the graph here. There's no part of the graph over here, no part of the graph over here. So just one solid piece, so there's going to be one interval. The left end, the low end, is at 5/4, comma, the high end or the right end point is at 2. And we saw that 5/4, 5/4 is not a solution, so we put parentheses on that. And 2 is a solution, so the rectangular bracket, right, make little 90-degree angles here. Try not to rush these, because if you rush them, it makes it look like curvy in parentheses, and the parentheses has a totally different meaning than this rectangular bracket. So again, try not to rush things. Great. All of these things, right, say the same thing. They describe the same set of numbers, and all of them represent the solutions of this inequality. And if you want to check it out, do a little test. Pick a number in this set here. Now obviously 2 is in here. That'd be easy to check. 4 times 2 is 8. 8 minus 5 is 3. 3 is greater than 0 and less than or equal to 3. It works on both. So 2 is a solution. Pick like 1.5, right? Anything between 1.25 and 2 will also work. And try it out yourself. Put in 1.5. 4 times 1.5 is 6. 6 minus 5 is 1. 1 is greater than 0, and 1 is less than or equal to 3, so that works too. 1.5 is a solution. Try anything you want in here, and it should work out. Should make both of these a true this whole statement true. Wonderful. So again, very easy and simple to keep these compact inequalities like this, and get the variable alone in the middle. All right, so I have one last one here. Another compactly written compound inequality. where we have 3 is less than or equal to negative 2x minus 1, and, right, remember, anytime you see these compact inequalities, the word and is involved. So 3 is less than or equal to negative 2x minus 1, and negative 2x minus 1 is less than or equal to 11. Again, you can split them up if you want, solve each one individually, and then find the intersection of the solutions. That's fine. But you're going to be doing the same steps in both of them anyway, so why not just keep it together and solve each one at the same time. Alright, just get the variable alone in the middle. Alright, so if I were solving the left one, 3 is less than or equal to negative 2x minus 1, first thing I'd do is I would add 1 to both sides of that left inequality, and I'd do the same thing to the right inequality as well, add 1 to both sides. Alright, now that's just addition. Alright, so the inequality directions are not changing, these symbols are not going to flip over. So this is 4 on the left, 3 plus 1 is less than or equal to, I'd have negative 2x still in the middle, and that's less than or equal to, and then 11 plus 1 is 12, right? Alright, and then again, if I were solving the left inequality for x, I would be dividing both sides by negative 2, right, to get rid of that negative 2, give me a 1x. Divide this by negative 2, and the same thing with both sides of this right inequality. So dividing all three parts by negative 2. Now here's the tricky part, right? Here's the thing you have to be careful with. Remember, in an inequality, when you multiply or divide both sides by a negative number, which I am doing for both of these, the direction of the inequality changes. The symbol flips. So this here is now negative 2, right? 4 divided by negative 2 is negative 2. Then this, instead of being as less than or equal to, will now be is greater than or equal to. Right, the symbol will flip because I divided both sides by a negative number. Middle part still x now. Divide the negative 2's cancel. And again, I divided both sides of this inequality by a negative number. And when you multiply or divide by a negative number, the inequality changes direction. So instead of is less than or equal to, it is now is greater than or equal to. Right, so the direction of both of them changed. And then 12 divided by negative 2 is negative 6. Okay. And here are the solution. Here's a description of the solutions. The variables along the middle. And this is great. This is saying x is between negative 2 and negative 6, including negative 2 and negative 6, because you got the or equal to's on both of those. Just typically these compact inequalities are written so that the smaller, so that it's in the direction of, the smaller number on the left, the larger number on the right. And negative 2 is actually larger, you can see is greater than negative 6. So I'll write that little note for you. Typically, a compact inequality such as this is written in that form that I had up earlier. A is less than x is less than b with a less than b, right? Where it's all less thans. It's in the direction so the smaller number is on the left, the larger number is on the right. Alright, so if you want to, this isn't wrong. Alright, what I have here is not wrong. The numbers that are solutions to this inequality are numbers that are less than or equal to negative 2 and at the same time greater than or equal to negative 6. But we can switch this up. Instead of instead of writing it this way, I can read it from right to left. So if I read this from right to left and write it out as I read it, this is negative 6. Negative 6 is less than or equal to x, and x is less than or equal to negative 2. Okay, that's if I read this from right to left and then wrote it down as I read it. So this is how typically you're going to see these compact inequalities, right? And this is like the previous two examples, where again the smaller numbers on the left, the larger numbers on the right, and yes, negative 6 is indeed less than negative 2. This is okay. Alright, and then for everything else, right? So now that I have a description of my solutions, let's do all three parts. Pardon me. The graph. Alright, so here's a number line. And throw 0 somewhere, and The numbers involved here are -6, which is to the left of 0, right? It's negative. And then -2 is bigger than -6, right? -2 would be closer to 0 than -6. It's considered larger, right? And then this is all the numbers in between them and including them, right? -6 is equal to -6, so it satisfies both. -2 is equal to -2, so it satisfies both. So -6 is in there, -2 is in there, so I have nice solid points above them, and every number in between is also in this set here of solutions. Great. So there's a graph, and we'll do our set builder notation. All right, write the same set of solutions as a set with a description of the numbers. So the set of all the solutions, right, is all the values of x, right? So all the values of x such that, right, as long as, and then x is between and including -6 and -2. I just write my little description here in the description here, the area here describing the solutions. Wonderful. And then finally, our interval, which is just like the previous two examples, right? There's only one piece of the graph, right? There's only one piece of this graph. There's no piece over here, no piece over there, so I'm only going to be writing one interval. And this piece has a left end of -6, comma, and then a right end of -2. And then are these end values actually part of the set? All right, this is everything from -6 to -2 is a solution. And we have seen that -6 is a solution. So again, one of these rectangular brackets. And -2 is also a solution. So again, another rectangular bracket, and you get what's called a closed interval here, a closed set. Great. And if you want to try it out, test it out, pick any number in here. Pick any number in here. Plug in -6. Plug in -2 for x. Plug in -5, -4, -3. Anything else, -pi, -2.17, -5.998, anything you want between these two or including these two, and this should be true. All right, so I'll just pick one, just one for now. How about -3? All right, if x were -3, well, what's -2 times -3? That's +6. 6 minus 1 is +5, and 5 is greater than or equal to 3. It's greater than. And at the same time, 5 is less than 11. Less than or equal to 11 is less than 11. So -3 is a solution that works. And again, try it out with anything. Plug in whatever you want in this set, in this set, in this set, and you'll get this being a true statement. All right, great. All right, so that's all I got for you on this particular topic. And as I like to say at the end of this, try the best you can to learn the material, understand the material on your own before you go looking for help. I find that people tend to remember things better for longer if they've taken the time and put in the effort to learn it on their own. So read the material, of course, read the author's examples, perhaps even try to work on solutions to an example before you read how the author did it, and then compare your work with the authors and see if you can learn anything from that, where you went wrong, learn from mistakes. Of course, work on plenty of practice problems and exercises and check solutions wherever they're available to see how you're doing. And don't just give up after the first approach at a problem, the first attempt, because there are often many ways to approach a problem and still solve it in mathematics. So, if after several attempts at a problem you're still not getting it, it's still not making sense to you, maybe you should go back and read the material again, more deliberately, more slowly. Take notes, take your time, because if after doing several problems or trying several problems, you'll have a better idea as to what the author wants from you, and then a second read through or even third read through of the material, you'll probably catch some things that you didn't catch the first time, or things will make sense that didn't make sense the first time through, and it'll make working on the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at problems, it's still not working out for you, still not clicking, still not making sense, then it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone in the class who you know knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos on the subject, such as this one, or and I'm sure there are plenty of other videos on these subjects I'm doing that are better than mine. I know you can find videos better than mine out there. They're out there, easy to search for. But just keep at it. Stay persistent. Keep practicing. Don't give up. And I think the hardest thing is to have a positive attitude. You know, don't don't go in automatically assuming you're going to hate something, because that just ruins it right away, and it keeps it ruined the whole time and makes the learning experience terrible. Um, try to have an open mind. Try to think that I'm going to enjoy this. I'm going to go in and learn something today. I'm going to enjoy learning it. I'm going to take something from this that I can use in my life, and everything's going to be great. Again, very much easier said than done, but you'd be amazed at the difference that a change in attitude can make. So stay positive, keep practicing, stay persistent, don't give up, and I just know you can get it. And thank you very much for watching.